Welcome, Shaler area, to note video number 8. We can finally start talking about the periodic table. Alright, so we got to start where it begins. So the history of the periodic table, around the mid-1800s, we knew that there were elements. So we kind of knew that there were these substances on Earth that seemed to be the most basic things that were around. And if you took more complicated things and kind of broke them down, we would end up with these basic structures. And scientists knew about 60 of them. So, I mean, nowadays there's a bunch. We're up over like 100. But back then, we only knew about 60 of them. And remember, science is all about finding the patterns. And scientists were really struggling because they were looking for patterns and they couldn't find them. And then along comes Dmitri Mendeleev, and he was obsessed with the elements. He would think about them all the time. He created like a deck of cards that had all of their properties on them, and he would like play with them constantly and organize them in different ways and try to figure things out. And he is the person who put together the elements in the order, well, I'm not going to say he put them in the order that we use today, but he is the first person to recognize the patterns in those 60 elements. And we call it the periodic table because the word periodic means that there is a repeating pattern. As the story goes, he was sleeping one night, and the element, because he was constantly thinking about these elements, so he was sleeping one night and they were just going through his head, and in a dream he sees the structure of the periodic table. So he gets up and he grabs his cards and he lays them all out, and what he did was he ordered the elements by increasing mass, but arranged them so that they were in columns where they had similar reaction properties. He left spaces, which was the real genius of his organization here. He left empty spaces and said, this spot will be filled. We just haven't discovered the element yet. So he was future thinking enough and was confident in his patterns enough to say, there is something here that has yet to be discovered. And to his vindication, because he had a lot of people that were naysayers and saying that he didn't really figure things out, all of the spaces that he left, all of the things that he predicted, ended up being filled. It wasn't perfect, though, and that's why I said he didn't create the table the same way that we use today, because there were some outliers. There were some elements that didn't quite fit into the pattern. And he even had some that he predicted that were wrong, like the data about them were wrong. Like this has been reported to have this mass, because remember he put them in order of mass, but that doesn't make sense, so that must be wrong. And when they went and ran the experiments again to try to get the mass of that, he was correct. The masses were wrong. Made a lot of people unhappy because he was telling them that they were wrong. So this is an early version of Mendeleev's table. So these would be, like if you turn it sideways, it actually more resembles the table that we see today. But later on, more early 1900s, that thing that was just there was turned into this. And this looks a lot more like what we're used to. We have the groups, group 1, 2, 3, 4, 5 all the way across. We have the periods or the rows that go down the side. And we have these elements. And these lines represent the spaces that he was leaving, that he was predicting there would be something to fill it in with. So Mendeleev laid the groundwork, but Moseley is the one who actually put the elements in the order that we have today. Now, Moseley figured out a technique that allowed him to know how many protons there were in an atom. So I don't know what his experiment was or how he did it. I'd have to do some research into that. But he was able to deduce the number of protons in the atoms of those elements that we know of, and he rearranged the table so that instead of being in order of mass, now they're in order of proton number. That's what we call the atomic number today. And this eliminated all of those outliers that Mendeleev didn't quite match up with the right columns that he would want them to go in by putting them in order of mass. If you rearrange them by proton number, by atomic number, now this is what we call it, worked out great. He was brilliant, but if you notice, he didn't live very long. This was, do you know what world event was happening right around this time? Yeah, that was World War I. And Moseley got called up to be in the army, and actually he was a part of the Battle of Gallipoli, which was a battle that was happening when the Allied side was trying to invade the Ottoman Empire to try to get some of the pressure off of the Western Front that was happening with all the trenches. They tried to attack from the other side and kind of come at the flank, and they invaded the Ottoman Empire at Gallipoli, and well, that's where Moseley died. It is said that this work, I mean, absolutely, he would have won the Nobel Prize for his discovery here, but you can't win the Nobel Prize posthumously. So since he passed away before he would have been awarded it, he doesn't get the Nobel Prize. So these are the stats about atoms that you're going to need to know. One of the things is called the atomic number, and that's always found up here on the periodic table. It's the order that you see them in, like element 1, 2, 3, 4. That's the number of protons in that element. Now it's also equal to the number of electrons, but that's only in atoms that don't have a charge. And most atoms, when you think of them, are well balanced. You would have seen that in the element builder gizmo, that if you have the same number of protons and electrons, you have a neutral atom. And that's what most atoms are going to be like in the world. Now, if you do tinker with the number of electrons, you end up with an atom with a charge, and that's what we call an ion. So an ion is any element or any atom that has an unequal or an unbalanced number of protons and electrons, so they're not balancing their charges out equally, and you end up with an atom that is charged. So every proton gives the atom a +1 charge, every electron gives an atom a -1 charge. So in this case, for nitrogen, for example, we have 7 protons and we have 7 electrons. Well, let's say we add another electron to it. So now we have 7 protons and 8 electrons. That means we would have 7 pluses and 8 minuses. So after you balance them all out, you would end up with a -1 charge. The mass number, which isn't one of the things up here on the chart. So you don't see the mass number on the periodic table. But the term mass number refers to protons plus neutrons. Atomic mass is this number down here at the bottom, and it's always a big long decimal because it's an average. The mass number is the average mass of all of the atoms of the element, we'll say, in the universe. Now, you realize you can't go around the universe and get all of the atoms and measure them, but we take a big sample of, say, carbon, and we measure the masses of all of them, as many as we can. Now, atoms have different numbers atoms have different masses because they have different numbers of neutrons. So every atom of carbon has to have 6 protons. That's what makes it an atom of carbon. If an atom has 6 protons, it is carbon. That's where an element gets its identity. Its identity comes entirely from the number of protons. Its charge is then determined by the number of electrons, but electrons are really tiny, so they add almost no mass to the actual element or the actual atom. Neutrons, though, do. Neutrons are quite massive. They're a little bit bigger than a proton. So to figure out the mass of an atom, you add together the protons and the neutrons. That's where that mass number comes into play. So let's just round this off to the nearest whole number. So we'll say it's 12. If that's 12, and we know 6 of them are coming from the protons, then how many neutrons are there? Well, there's another 6. 6 plus 6 is 12. But some carbons don't have 6 neutrons. Some carbons have 5 neutrons. Some carbons have 7 neutrons. Some carbons have 8 neutrons. Some carbons have 9 neutrons. And that changes the amount of mass. And if you average together all the masses of all of the atoms, this is what you get. And that means most of them have 6 and 6. 6. But some of them are going to have more. Some are going to have less. 6 and 6 is 12. 12 plus 6 is 16. 16 plus 6 is 24. 24 plus 6 is 28. 28 plus 6 is 32. 32 plus 6 is 36. 36 plus 6 is 37. 37 plus 6 is 39. 39 plus 6 is 40. 40 plus 6 is 50. 50 plus 6 is 55. 55 plus 6 is 60. 60 plus 6 is 70. 70 plus 6 is 80. 80 plus 6 is 90. 90 plus 6 is 100. 100 plus 6 is 200. 200 plus 6 is 300. 300 plus 6 is 400. 400 plus 6 is 500. 500 plus 6 is 600. 600 plus 6 is 700. 700 plus 6 is 800. 800 plus 6 is 900. 900 plus 6 is 1,000. 1,000 plus 6 is 2,000. 2,000 plus 6 is 3,000. 3,000 plus 6 is 4,000. 4,000 plus 6 So here's the actual breakdown of carbon. You can have isotopes of carbon that range from 8 to 16. So if you have carbon 8, that means it's going to have 2 neutrons, because 6 plus 2 is 8. Although if you have 10 neutrons, you would get carbon 16. And they can be anything kind of in between. Now, the further away you get from the middle, the more rare they become. 98.93% of every carbon atom in the universe has a mass of 12. We call that carbon 12. A little bit more than 1% of all the carbons have a mass of 13. So how many neutrons would they have if they had a mass of 13? Well, 6 plus what is equal to 13? So that'd be 7 neutrons. And then we start to get to the really rare ones. So 0.0000001, one atom in a trillion of carbon atoms, is carbon 14. And this is what we often use to date things. We talk about carbon dating. So if you average all of them together, including the ones that go all the way down to carbon 8 and all the ones that go all the way up to carbon 16, which get really rare, you end up with a mass, an average mass of 12.011. That's where we get our atomic mass on the periodic table. So some quick check questions. How many electrons would a neutral atom of oxygen have? How many electrons would a -2 ion or a -2 ion of oxygen have? And then one last question. Are there more isotopes of oxygen 17 or oxygen 15? You would figure that out by looking at the mass number and deciding where this number came from. And that's it. We've got 10 questions on this booby trap, and I will see all of you next time.